Hello and welcome everyone. My name is Peter Robinson, and today I've got Matt Krak from LayerZero, who's here to tell us about their technology. So Matt, do you want to introduce yourself a little bit and before diving into your slides?
Sure. Peter, thanks so much for having me. Very excited to show everybody today what we've been working on over the past now 2 years, which is crazy to say at LayerZero. From our end, I'm currently working as developer ecosystem lead at LayerZero. So I work really closely with our developer relations team, mainly focusing on tooling, contract libraries, getting developer feedback, and helping you guys just build applications faster on top of the protocol. And mainly, this talk will be focusing at a high level on what is cross-chain messaging in general? Why do you need LayerZero as an arbitrary message passing layer? Why would you choose LayerZero over some other cross-chain platform? And going a little bit deeper and diving into some of the unique applications that you can build. So super excited. If there's anything else, happy to go, but let's jump right in, right?
Yeah, sounds good. And so should people just ask questions via the chat, or are you going to ask people to ask questions at the end of each section? What do you prefer?
Yeah, feel free to throw any questions you have in the chat, and I'll also stop intermittently between slides and just try and catch up and ask if there's anything that you guys have in particular to ask about.
Sounds great. So please share your slides.
Awesome. So I think we took care of the introduction out of the way, but if you'd like to follow me on Twitter, feel free to. Again, I think going and focusing on cross-chain at a high level, right? Bridges and bridging arbitrary message passing layers, main, value add that you can clearly see from them, right? You're connecting isolated groups of people. It's no different with blockchain or the real world. You have, segmented groups that have information on each side, but no way of communicating across what it is. And so by unlocking with a bridge that flow of information, you're able to suddenly coordinate the transfer of goods and services, and more broadly speaking, for blockchain technology, the coordination of financial services. I think most of us here who are tuning in probably have some conception of cross-chain as being part of the developer stack that you can use when building on a blockchain, right? We know that in general, each blockchain has some type of inherent characteristics, and there are trade-offs that you make between them, right? But I don't know if it's as clear to a lot of people how this works at a low level and some of the challenges that kind of arise from working on multiple blockchain environments. Right here, pictured, is just a simple ERC20 transfer on a single blockchain, Linea, for example. But this could be any EVM equivalent blockchain. We like to think of sending tokens, right, as moving them around, but really all we're doing, right, is updating the ledger itself, a mapping saying we're taking tokens from this user's account and crediting them to another user's account. And this operation is fairly straightforward because of, one, the blockchain's consensus mechanism, but two, the fact that everything is happening atomically. As soon as you get to more than one blockchain, this user flow becomes a lot more complicated. For starters, one, to have that transfer event actually work, you need to be able to call a function and confirm that it's been debited correctly on the source blockchain. From there, the user has to wait and hope that this message can then be pinged over to the destination chain and be received by the intended address or user or application. But this leads into a couple gray areas, right? One, what happens if things go wrong and someone takes advantage of that mint authority, the ability to just create tokens out of thin air and credits way more than was debited on the source chain? Suddenly, you don't have a unified supply of liquidity across all networks. And so, broadly speaking, the way that we came about solving this was through monolithic bridge security. And you can think about monolithic bridge security in a couple ways. You could think about this as a centralized provider that listens to events on a source chain and then writes them directly to the destination. You can think about this as a arbitrary message passing layer, right, with different verifiers in the center that are all required to verify that this event has happened on the source chain and write it to the destination. Or you could think about it as a middle chain bridge, where there is an entire separate blockchain in the middle that has its own consensus mechanism to validate that messages are actually being provided fairly and accurately from the source chain and then routed to the destination. And broadly speaking, all of these services and applications have been very, very helpful to the overall developer experience, right? This graph is from the Electric Capital Developer Report from 2023, and it shows that while there's still a majority of developers in the blockchain ecosystem that deploy on only one blockchain, this number has been growing, and more people are starting to become comfortable deploying on more than one chain, about 34%. But there's still some work to be done here, right? If it was so easy to start building cross-chain applications, you'd think that everybody would be doing it. The reality is we actually have to think a lot more about what happens when things go wrong. And this is something that I think is a mindset for most smart contract devs, right? Whenever you're building your application, you're immediately or hopefully in the mindset of thinking, how can I break this? And it's no different with cross-chain messaging. Although we'd like to think that all of the security can be, pushed to some third-party provider and we don't have to worry about it, we can inherit their trust assumptions and know that their security works. In the past, security has failed for a variety of reasons when cross-chain messaging. A couple of them can be, one, that let's say the platform is flat out centralized, and so anyone can come in at any moment and write what state is using the message passing layer. Other opportunists have found ways to find vulnerabilities in the client software itself of, let's say, different validators and then compromise the validator network. Other times, the protocol itself is just upgradable and the interface breaks. And because the interface has a vulnerability in it, someone who's quick to notice and pick up on the fact that the code is vulnerable will take advantage of it. But no matter what process a bridge gets compromised, the end result is usually always the same. Not only a single application, but every application building on top of that message passing layer is now compromised in some meaningful way. This historically has been why, if you look at the 5 largest hacks in the blockchain industry, right, 4 out of the 5 largest are all due to this type of monolithic bridge security, this ability for one actor or one lack of, I guess, decentralization to compromise the entire system and then compromise every application building on top of it. That's why I think of this analogy actually in a funny way. I hope if you haven't read the article Ethereum is a Dark Forest, I highly recommend it. But if Ethereum is a dark forest, you can think of cross-chain almost as a dark ocean, right? You have all of these blockchains, these isolated islands, right, that have their own consensus mechanisms. And the only way to know the state of truth is actually on the island itself. As soon as you leave the island, there's nothing confirming that this information is true. And so anyone can pass information through. And if a malicious actor controls the port and all of the waterways to get to that island, the island can face an existential threat itself. Similarly, if a centralized entity accidentally destroys the port, the island also faces an existential threat. And so you can quickly see between these two slides, right, that there is a huge amount of risk and a large attack surface when working with cross-chain. And so knowing how your cross-chain protocol works and understanding the security and the ways that you can prevent vulnerabilities is very, very important when working in this space. In general, with LayerZero, what we thought about is how do we actually maintain this global ledger, right? How do we provide interoperability and connectivity across all of these segmented, isolated blockchain environments in a way that is, one, permissionless, meaning that we cannot censor anyone who interacts with the protocol. Anyone can send a message at any time. They can have any application or externally owned account interact with the LayerZero contracts. 2, that once a message is emitted and is actually in flight to a destination, that LayerZero can't arbitrarily strike down a message that they want to. And 3, that this code is immutable. We don't run into the issue of someone accidentally implementing a faulty contract that has a bug or some vulnerability or attack vector we haven't thought of, and that compromises the whole system. This kind of brings us to something that's already been talked about within the Ethereum engineering group. So I'll do a quick refresher and kind of give you the spin on how it fits into LayerZero as a protocol. At the lowest level, you can think of it as omni-chain messaging or arbitrary messaging, right? The ability to validate that messages have moved safely from chain A to chain B. This layer obviously, helps guarantee that you can verify messages and gives you the certainty that this message is valid to execute finally on the destination chain, whether that's movement of actual raw bytes, whether that's movement of tokens, or whether that's movement of external function calls. LayerZero at a high level allows the application itself to choose the block confirmations that need to be weighted on the source chain, the required verifiers in what's known as a security stack, the optional verifiers of that stack, and a threshold necessary for a message to be considered verified. If you didn't catch all that, don't worry. We'll be diving a lot deeper in some of the following slides. But this is kind of the frame of reference for arbitrary messaging, right? The low-level verification of a packet moving from chain A to chain B. Once you know that a message is verified, you then have this problem of actually executing the message, right? The biggest pain point for a lot of cross-chain applications is that even though you've verified the message, it's not entirely true that it can be executed immediately for the user. If I click send on a source chain, what can end up happening for myself and for a lot of users, honestly, is that even though the message is verified, I then need to go have destination gas on that chain and be able to execute the message manually by connecting my MetaMask wallet or whatever means I have to then execute the message through to the destination. At a high level, LayerZero aims to solve this omni-chain function call layer by, one, giving the application control over the amount of gas limit, message value, and even the order of execution for an executor to use on these calls. If you look at the bottom here, there are kind of two workflows that I'm showing. The executor within LayerZero's protocol works as a way of, once a message is verified, it will automatically deliver the message to the destination receiver address. And after that message has been received successfully, a secondary call or a composable call, if you think about it, can be executed immediately after. The way this works is that when I pay for gas on the source chain, I'm quoted for this amount of gas limit and message value that I want to use. And then that gas is automatically swapped from whatever the native gas token is for the destination gas token, and then delivered to the execution address that I want to have. And so this enables you to not only seamlessly, from a user perspective, click send once on the source chain and automatically have messages delivered for me on the destination, but extend this logic further and further to have multiple and multiple composable calls that are satisfied as long as I pay for them on the source chain. The last bit to kind of jump into is the top level stack, right? The omni-chain application. This application layer consists of applications that have inherited whatever contract standards are necessary or are actively calling the send and receive mechanisms within their application logic, right? Typically, the way that this works is that you will take whatever inputs that you want to send and encode them as bytes, and then those bytes will be delivered and unpacked for you on the destination chain. Out of the box, LayerZero provides 3 different contract libraries to help you get started and build more and more complex applications. The OAP standard, which helps make it easy for sending these bytes arrays. The OFT standard, which extends the OAP and makes it easy for you to not only send arbitrary messages, but deliver an ERC20 token transfer to a destination chain. And then finally, the ONFT, which lets you move NFTs seamlessly between chain A and chain B. Again, if you have any questions, we're going to dive in a little bit deeper, so just stay with me. At a high level, this is the send workflow for LayerZero. Whenever any application wants to send a message to a destination chain, there are a few key factors that they're interacting with. The application will call the send interface on a LayerZero endpoint contract, and they'll specify 1, a message that they want to send, 2, a destination chain that they've deployed an application on, and 3, this send library config. What's happening in this workflow is that those bytes that I want to deliver from my omni-chain app are being passed through to the endpoint contract itself. And then that endpoint is using a configuration that I've set up beforehand, these message libraries. The way that a message library works allows you to basically configure what are the emission settings that I want from the source chain, namely the number of block confirmations that I want to wait before emitting this message, and 2, who do I actually emit this message to? One of the problems that we talked about earlier in the workflow, right, was that being forced into accepting verification standards that I don't own or control means that suddenly, if the protocol has some existential threat with their verification layer, every application is suddenly under threat too. This setup enables you to configure not only the size, but also the type of security that you use within your stack. So being able to not only control what security providers I want to use. For example, at the moment, we have LayerZero Labs running one of these decentralized verifier networks, or DVNs. We have Google Cloud running one, Polyhedra, a ZK Lite client, a lot more that I'll be getting into later. And this enables you to not only control the security setup, but also who's executing the messages for you on the destination chain. Once you've sent that message successfully, each of these different verifier networks have their own consensus mechanism for figuring out what messages are valid, right? Once they, each use their own internal process, they independently will write a message to the destination chain. And in that destination message, they'll be delivering a payload hash of the original message that was being sent. You can see here that this receive config is basically expecting and enforcing on the destination chain, one, the number of block confirmations that they waited, two, that it's coming from the expected addresses, and then three, that the adequate threshold set up by the application on the destination chain is correct. If all those things are met, verification is successful. Finally, once a message is verified, an executor can come through and deliver the message through to the destination app. The way this works is that the executor will first commit that verified nonce into the messaging channel, and then the executor will execute another call called LZ receive to the destination app using this receiver interface. So this workflow, being able to send on a source chain, be able to verify and validate messages on the destination chain, and then automatically execute through messages down to the application itself, enable you to have a very seamless experience from the user side while still maintaining a lot of the security properties that you must have when operating in a cross-chain environment. This kind of broadly brings us to what the framework for LayerZero is, this ability for any smart contract on any blockchain network to interact with a LayerZero endpoint on that same chain and comfortably know that they control all of the configuration steps to be able to send from that point to point without needing to worry about the protocol itself getting in the way. Diving a little bit deeper, I know I mentioned we were talking about what exactly is an endpoint, right? The LayerZero endpoint contract is a way for you to, one, interface with the protocol, and two, configure your application, right? The endpoint contract itself is entirely immutable. Once it's deployed, LayerZero cannot change any of the contract properties itself. The only thing that can change in the protocol setup are the configurations controlled by the application owner. And what this means is that not only do you have a stable interface for sending and receiving messages that's predictable on every chain, but it means that now you have the ability to guarantee that even into the future, this interface will be what I use to send messages to any future blockchains. At the same time, there is a very good cause for upgradability in the fact that, new best practices tend to develop in this space. And so how do we make it where there's a way to maintain this level of immutability and security while at the same time providing applications a future-proof path to, grow and expand and become better and better as time goes on? These appendable message libraries are kind of how LayerZero goes about solving it. At a high level, the message library is part of the verification stack for LayerZero. These message libraries are individual smart contracts that are appended into this registry. The way you can think about it is that each library itself controls the interface for emitting messages out from the chain itself. The endpoint controls the actual structure. So whenever I want to change my configuration on a chain, I will call this set config function and pass in a bytes array. Within that call, it'll be passed down to the message library of my choice. And based on the library that I've selected, it will determine how to interpret those bytes that I'm passing. So in this example, with LayerZero V1, the way that it worked was I would call this set config function, And using ULN V2, for example, this gave me an option of an oracle and a relayer that I must use. With LayerZero V2, we added this new message library, and this gave the opportunity to not only configure multiple different verifier networks that can, one, be required, some can be optional, and that threshold, but also this permissionless message execution, the ability to configure an executor to go and deliver both these receivable calls and also these composable calls on my behalf. And so this change from LayerZero V1 with this first message library to LayerZero V2 with a second library gave me the option to change how my application was emitting messages on the chain. And so I think I'll pause really quickly there, and just bounce back to this workflow, right? All of this concept of having a strong endpoint, of having configurable message libraries, and then also this concept of being able to configure them from the application side enables you as a user to not only know that, one, my security stack is based around the security assumptions that I have. I'm not forced to inherit any security assumptions that some other protocol may have designed. But two, it keeps it flexible so that it's not stagnant and that it never grows stale in the development environment. I think really quickly, are there any questions in the chat right now?
No, there. Oh, sorry. Go ahead. No, I thought I heard someone. Anyway, I don't think
Okay, cool.
we don't have anything in the chat, but I do have a question.
Sure.
So I could default, I could default to just choosing to, like use just one of the message providers rather than, say, thinking that I wanted to get, say, 5 out of 8.
Mhm.
Have you deployed this yet? And how many people chose more than one message provider?
Mhm. No, it's a great question. So it's been currently live since January, and we've seen a lot of variability in what the security stacks look like. I think from a couple issuers, for example, stable coins, right? Different stablecoin providers have chosen to use not only multiple DVNs, typically 3 or 4, but also they'll run a DVN themselves as kind of the master, right? And so the way that the security stack setup works is that if you look here, let's say there's 4 of them, right, that are selected in the stack. From there, let's say 3 of them are required to deliver a message to the destination chain. Some of the setups that we've seen are where the application owner will run one DVN that's always required to sign off, right? So the threshold for them is that they must deliver at least their signature, and it has to match what some of these other providers are bringing to the table. And so from a security standpoint, I think it's very unique in the sense that you're able to not only have, this kind of redundancy check built in that, hey, I trust that, this collection of signers are going to be delivering verifications correctly, but I want to have a sanity check just in case to make sure that in the worst case scenario, let's say that they're all 3, right, turn on me, the one that I'm running myself will always be guaranteeing at least a state that I know is true. And so this gives you almost a way to have a safeguard where if, let's say, the worst case scenario, right, each of these independent verifiers fall apart, I'm not bricked and my application users are not suddenly, at risk themselves. The other interesting thing from having the ability to configure multiple security stacks and kind of the size and shape of them is that suddenly you have a much wider space for, one, what is like the fee for a cross-chain message, right? And what are the security guarantees for that message? Not every application is going to have the same needs in terms of security and in terms the same needs for cross-chain messaging, right? A way to think about it is that LayerZero and kind of the protocol stack is giving you a way to have configurability at the application level for any type of cross-chain app that you want to build. And similarly, when you talk about a lot of smart contract development and security practice, ultimately, a lot of the risk lies on the application itself to, one, first think about how they can break their own security, and then two, understand kind of that risk assessment and then move forward in a way that prevents those vulnerabilities from occurring. One of the things that I think from at least the number of deployers that we've seen on Endpoint V2 so far is that protocols that are moving much higher volumes of liquidity typically tend to want to have higher security guarantees as part of their messaging workflow. Similarly, protocols that are moving much less valuable messages, at least in their mind, might lower the security threshold that they need for their application for the trade-off that it's a lot cheaper and gives better usability for someone who needs to send, let's say, 100 messages through for like a gaming application.
Yeah, that makes sense. Makes sense. Babu, did you have a question?
Yes, yes. Thank you. It's very interesting. So I can think about this like a stack of apps or application, and the application has some messages that need to be translated or that need to be ported to another network, and your protocol takes that message and then port it to the other network, right? So to interpret this message, say for example, each application will have a different type of message. Say I might carry one type of asset, and that is a message that need to be ported. So how does this message interpretation happens?
That is a great question. I'm actually going to jump into the next slide here really quickly. So going actually at the application level, right? How do we, standardize the message that's moving through the protocol? At a low level, most applications will use the endpoint send interface. This function here, LZ send, is part of our omni-chain application standard. So you can inherit this contract today and encode any of the inputs you need as bytes. The way that encoding works is typically through abi.encode, but because it's just a simple bytes array, you can be very creative with how you pack your message inputs. For example, the Omni-Chain Fungible Token standard uses this app standard underneath it to encode ERC20 token transfers amounts as a bytes array, and then on the receive side, decode those messages from the LZ receive function. This bytes call data format means that you're able to, one, have a max message size. I believe it's up to 10,000 bytes by default, but this can be configured too by the application owner. And really, figure out how you want to interpret that message on the destination chain, depending on your app's use case. As an example, I'll dive in a little bit later too into how the OFT does this with this message codec library, where they will essentially splice different bytes out of the message and use, let's say, the first 20 bytes, right, are a representation of the token amount being transferred. The next 32 bytes are for the receiver address, and so on and so forth, right?
Yeah. So basically, you are kind of giving us the message, how we wanted the message to be basically formatted, and then okay, it makes sense.
Exactly. Yeah. We provide you just a standard format for encoding, and then you're free to decode however you like in your smart contract.
Right. Okay.
Awesome. I'll keep going. Moving a little bit deeper, there's a bunch of security checks too from the application level that we try and have, at least for the protocol side. One of them is that you might have noticed in this workflow, there is an app on a source chain calling a LayerZero endpoint, and we'll call this chain A. And at the same time, there's another app deployed on a destination. So you have two smart contracts on two different chains. How do you know that you can trust them? This kind of brings in this concept of peers in the network. At the application level, we have within the OAP standard this function called setPeer. What this peer does is it takes an endpoint ID. The ID you can think of is just the identifier for this specific endpoint on this specific chain. And you can create a mapping using this app standard, right, that essentially will have you list what are the peer addresses on every other chain that I want to connect to. And what this does is that it will enforce that during the execution logic, it will check, is the origin this message is being sent from the actual origin that's a peer of this application? We'll get a better demo of what that looks like in code, but from a high level, you can think of this as essentially you defining on the destination chain what you want the source addresses to be and where they're coming from per endpoint ID. This enables you to guarantee that there's not some unexpected execution within your application from an unwanted sender that's spoofing messages, right? Or doing something that might be malicious or unintended that could break your application logic on destination. A little bit deeper, you can kind of see how the send interface works itself. Within this LZ send function, some of the inputs are this destination identifier, the message as bytes, this option setting, which I'll get into in a little bit here, the fee that I'm going to be paying to deliver the message, and then a refund address just on the source chain for if this call fails, right? But the main thing to pay attention to is that all this send function is really doing under the hood is it's calling the endpoint directly, calling send with an amount of message value, and then it is enforcing that there is also a destination peer that I'm sending to. So this gives you a really good check. You have a check on the destination chain to make sure, hey, am I actually receiving messages from the peers that I expect? And on the destination chain, or sorry, on the source chain, making sure that you are enforcing that there is a destination to send that message to. So creating this channel between applications, essentially. Let's kind of take a step back here. I've thrown, I think, a lot of concepts at you, and I want to just walk from a high level how this kind of fits into that token transfer workflow that I mentioned at the beginning. If a user wants to move 100 tokens of, let's say, this OFT contract, right? This OFT, Omni-Chain Fungible Token, is an ERC20, and it just comes with a couple helper functions. Namely, when I call send, it will invoke this debit method that takes an amount of local decimals, a amount of a minimum amount for slippage, the destination that I want to send to, and it will encode this information as bytes to send through the LayerZero endpoint. This application owner here will have selected a collection of different decentralized verifier networks to include in their security stack that ultimately verify the message on the destination chain before an executor comes, executes the message from the LayerZero endpoint, and then a credit function is evoked that tells us who to send the tokens to, what is the amount to send, and what is the source endpoint ID it's coming from for that peer check. Once all of those things have been submitted, the source transaction, the verification step, and the execution, you have a seamless distribution of tokens, 100 debited from the source chain and then credited on the destination, all from one click from the user's perspective. And taking a higher level step and kind of diving in a little bit deeper, what this means is that in the worst case scenario, the event that we talked about earlier, where let's say a decentralized verifier network fails outright, the worst case scenario is no longer that, one, every application is lost. Not true. Actually, the only thing that could be stopped potentially is your application specific message logic. But two, even if, let's say, one verifier goes down, if I have my configuration set as 2 out of 3, for example, it means that messaging will not even be affected by this one verifier going down, and I can seamlessly swap in another verifier network to take its place or remove it from the stack entirely until I've addressed what the problems are with that network. And this gives you a much better framework in general as an application owner to kind of deal with a lot of the security attack vectors that are in the space. You don't have to rely on trust assumptions that you haven't set. You don't have to rely on the protocol itself rugging you from some upgradability. Everything is configurable within the application logic itself, and it gives you a blend of immutability via the LayerZero endpoint, while still giving you future-proof likeness with these appendable libraries that handle what type of configurability I can select. None of these things are enforced by the protocol. They are entirely enforced by the application owner. Diving a little bit deeper into the decentralized verifier networks and some of the ones that are live right now, I believe today there are over 30 plus different DVNs that are live. And what that means is that you can have a very unique security setup when it comes to your application. You can have a combination of polyhedra, which is a ZK light client that is creating ZK proofs of hundreds of thousands of transactions to validate that they happened on a source chain. You could have a geodiverse validator set that Nethermind is providing. You could even combine it with, let's say, an established Web2 entity like Google Cloud, and combine that with another messaging provider like Chainlink, CCIP, or a middle chain bridge like Axelar, and build a very unique security setup that, one, you don't have to learn an entirely new protocol stack for. You just have to configure an address, which is much simpler from the application side. And it means, broadly speaking, that not only can you support any verification schema within your application, but it also means that you suddenly can create these diverse stacks that play off of each other, right? The odds of a middle chain bridge colluding with Google Cloud and also colluding with a ZK Lite client are probably very, very, very slim. And if all three of these things happen to collude at once, there's probably a much worse outcome actually happening for every chain than we would think, right? So this gives you a very, very unique way of customizing your security based around what your application needs and what your assumptions are about the current state of the blockchain industry. Diving a little bit deeper into how kind of configurations work from the block confirmation side, right? The ability to control how long you have to wait before that message gets emitted enables you to protect against blockchain level reorgs on the source chain. So let's say that, you know, you send a message, emit it, but the state gets reversed back because of a block reorg on the source chain itself. This gives you a guarantee to know that, hey, finality has happened. I've reached the amount of time critical to know that my message is included on the source blockchain before going and doing any extra options and delivering messages on destination. Secondly, some other things that you can control, like I spoke about earlier, being able to understand the security stack, configure the required, the optional, the threshold of verification needed for a message to be delivered. Super, super paramount for just making sure that, you know, you are avoiding kind of these situations where faulty or malformed messages can be delivered. You can also control the execution logic. So like I brought up earlier, when you send a message on a source chain, you only have to pay in native gas token. The way that it works is that you can configure an executor as part of your setup. By default, LayerZero runs an executor as a production asset. And the way that this works is that whenever I want to send a message to a destination chain, I will figure out within my application how much gas that I want to deliver, that gas limit and message value to the destination chain. I will then pay a small fee for the executor to automatically swap my native gas token for whatever the destination gas token is, and then deliver that message through to the app that's receiving. But the nice thing about this is that this executor is not a required element of the ecosystem. Not only can you decide not to use LayerZero's executor, you could run your own executor. You can actually turn it off entirely, as this bottom workflow shows. So a user will pay only the source gas to, you know, send the message and pay for the source blockchain to emit it. And then the user can go and do that manual execution step that we talked about earlier if they desire, by just calling the LayerZero endpoint directly. And the way this works is, you know, what we showed before, the ability for these different verifier networks to confirm the payload hash that has to be executed. And then once that message has been verified, you know that it has to be that payload delivered. And so any user at all can go and deliver that message on their behalf. Diving in a little bit deeper into the gas settings, there are a plethora for you to pick between, a lot of configurability here. Again, like I mentioned, you can supply the gas limit and message value for, let's say, the first leg of my transaction, wanting to deliver some receiving payload to my destination app. And then from there, if I want to, I can specify those external composable calls that happen afterwards, each with their own index. So let's say I want to have more than one, and price the exact gas limit and message value to be delivered per message. Really, really useful for if you have a, you know, very complex app on the destination chain that has to make a lot of external calls, but needs to ensure that, let's say, all execution logic has been satisfied in the receive step before moving forward, and for ensuring that if there's a failure somewhere along that chain of composable calls, you don't have to have everything atomic where it will all revert at once. Instead, you'll have this opportunity to have it be executed for the LZ receive step. And then if, let's say, there's a gas issue with the compose logic, you know that the first call still succeeded. Besides that, you can still dive into more looking at nonce ordering. LayerZero allows you to control the order of your messages. So from the source side, you're able to, by default, have unordered messaging where if, let's say, a message fails to execute, to be clear, after already being verified, subsequent nonces can continue to be executed, and subsequently have order delivery toggled on if you'd like, for, let's say, if you need an application that absolutely knows the intended order for governance votes, for tracking airdrop criteria, for tracking whatever it may be for your application on the destination chain. It can be really, really useful to know that if nonce 2 fails for some reason, nonce 3 and 4 will halt and be paused until that message is retried and executed to ensure that the order and validity of messages match what happened on the source chain and is delivered correctly on the destination. Again, max message size is something that you can configure as well. The ability to control how many bytes that you want to have as the target message. This can be useful for, again, making sure that when you deliver to your destination app that these messages aren't malformed and follow the proper spec of whatever your bytes array looks like. And then again, finally, just diving into the composability step, making sure that you're able to ensure separate atomic pieces of your destination execution logic, right? The ability to, for example, send tokens to a destination address and then be able to immediately swap those tokens for another ERC20 contract, right? The way this works is that the receive step has its own gas limit and message value. So this execution logic will execute atomically on its own. And then a call will be made back to the LayerZero endpoint and delivered to the destination app for the second composable leg of the transaction. Again, entirely separate. If this call fails, this call still succeeds. And really, that's kind of the breadth of all the configurations you can do. I feel like at this point, I may have added a little bit too much to go into. So feel free to stop me right now if there's any questions about anything related to the configuration stack or the DVNs. Happy to go through what each of these mean in a little bit clearer detail.
So I think we've got a few questions in the chat there. So why don't we maybe go through them? So
let's do it.
Yeah, let's do it. All right, there we are.
The architectural changes from V1 to V2. Yeah, we'll start there. Really, really good question. So I'll go back a few slides. Architecturally, there are a couple new things added from the endpoint side. So remember that the endpoints themselves are immutable, right? Once a LayerZero endpoint's deployed, it can't be changed. And so the big difference between V1 and V2 is mainly that the V2 protocol uses new endpoints that we've deployed. The way that these endpoints work, they're still immutable, but they have slightly different interfaces that we've made based off of developer feedback over the last year. So the endpoint V2 interface, in my opinion, is a lot simpler to interact with. There have been some optimizations made for, one, making it easier for you to deliver more complex payloads. A lot of that composable logic that I've been mentioning about, the ability to pack more and more calls, is really one of the things that we added for endpoint V2 to make it more future-proof and just have better composability from the traditional way where you pack all of your calls into one function, and then once that function is executed, you hope that all of them are delivered. But if one fails, the whole thing reverts. The endpoint composable logic was made to have it where you can have these independent legs of the transaction execute. And if one call reverts at the very end of this sequence that I have executing, it doesn't cause every previous message that was successful to revert. And ultimately, it makes the debugging a lot easier for you as a developer. It makes the message workflow a lot more extendable. And that was like one of the key reasons that we built out the endpoint v2 logic. One of the other things I'll share too, if you want to follow along afterwards, is this docs page that I wrote. I'll just share it in the chat here. This just gives a v2 overview going through, this idea of how we expanded to from the Oracle and relayer setup in v1 to this combo of security stack and executor, and then also these new protocol contracts for the message libraries and for the endpoint interface to kind of just make things a little bit clearer interface wise, and also improve message throughput overall. From the message throughput side, it's also interesting. We moved from v1 being ordered execution, which is what I showed, I believe, here at the end. Previously in LayerZero v1, all of the message ordering was ordered by default. And this was an assumption that we made when we first released the protocol. We initially thought that every application would want to have it where if a message is sent from the source chain, it will be executed in that order on the destination. But what we found out is that for things like token transfers that might be entirely unrelated, right? For, let's say, a fungible token like in ERC20, you don't actually need the ordering of the execution to match. The only thing you need is for the verification to be, ensured up to a given nonce. We can dive into kind of how the nonce enforcement works at a deeper level, but I think this probably suffices for the question, right? Nice. Is the DVN network running the same logic? If so, how can we make sure they won't hit a vulnerability at the same time? Yeah, really good comment. So the way that the DVNs work is actually very interesting. They're not all using the same client to run the DVNs. So, for example, Polyhedra ZK Lite client is entirely built in-house by their team using their ZK bridge. Similarly, for Chainlink CCIP, Axelar's middle chain bridge, they're not using the same client software to move messages through the network. If you actually look at a low level, for example, when a application is using CCIP or Axelar, you can follow the messaging logic and see within CCIP or within Axelar how they move the message to the destination chain. And so really, all these DVNs, all they're doing, and probably should have started with this slide actually, all they're doing is writing, their interpretation of this source payload to the destination message library. They're just writing that payload hash using their own mechanism. So Polyhedra's ZK bridge is writing here. Axelar could be writing to this message library. CCIP could be writing to this message library. But what it means is that you have complete independence, essentially, on the verification logic. And that gives you, one, the strong guarantee that they're entirely separate and unique processes. They're not all based on the same client. But two, if you want to run your own DVN, you're also introducing more randomness into the security stack, which can potentially actually help security by making your providers more independent. So I hope that answers the question. A smart contract can't sign on its own behalf, so are you relying on the trusted messengers via the source or on the user to include information in a message signed by them? Yeah, good question. The send logic is ultimately up to the application. I'll dive into some code examples in a sec, but essentially you define an interface, right, for what are the inputs that this user is going to send. For the OFT, that input is typically, on the contract level at least, a amount of tokens and amount of ERC20 to send to the destination. It is the amount of gas that I want to pay for on the destination chain. Typically, an OFT can enforce the amount that they have to send at the application level. So that helps with preventing, underflow of gas to the destination and failing execution. But generally speaking, for smart contracts, right, you define the interface of whatever inputs you want a user to provide, and then your contract will do the encoding logic to turn those inputs into the bytes array and then deliver that bytes to the destination to be decoded. I hope that is clear to everybody. Awesome. Anything else, or I'll keep going and we can jump into maybe some code examples.
I have one. It's not a question, just about an opinion. So
Yeah.
we have this token transferring one to another, right? And you
Mhm.
have some gas cost in both the chains at the moment, right?
Mhm.
But
Yes.
is there any way that we can avoid the gas cost on the minting chain? Say for example, we have to destroy the token on the source chain, right?
Mhm.
That includes some cost because it need to verify that is yours. That we can agree that that's a cost involved. But for minting, it's
Right.
a quick minting, right? So
Mhm.
can we have a mechanism where we can, that's how bank work, right? Banks depositing, there is no money, it is depositing, right? So can we
Mhm.
have a mechanism where minting is no cost, so mint? Then
Mhm.
this problem of you have the problem of transferring that native coins and everything will be solved, right?
Definitely. The reason that it's difficult, I would say, in the current, cross-chain environment is that every chain has different opcode cost, right? And so the way that you actually derive at, what is the cost of executing these functions versus these other functions on chain is derived by what opcodes within the environment they're invoking. To send a message, ultimately, you have to ping these on-chain elements, namely the DVN contracts on the source chain and the executor contract on the source chain so that they know to emit the message. But actually, we've seen a couple people do some interesting work with account abstraction to have this type of gas payment abstracted from the end user, right? It can be paid for by whatever the application is on their behalf, either through some balance it's pulled from, whatever it may be. And so, as an application user, like I totally agree, having to pay twice to write a message on source and on destination doesn't feel like great UX. But I do think that, as gas costs get cheaper over time, at least with, a lot of the work being done with blobs, and as, account abstraction becomes more and more viable, you can probably reach a state where cross-chain messaging can be done incredibly cheap for the end user, with just the application owner or organization taking on maybe a brunt of those costs. But I think in general, it's always going to be difficult because you have a cost of block space, right? So there's always going to be a cost of including on the source chain and the destination. It's just about driving it so low so that no one really knows it's there.
Yeah, this could be something that new chains can adopt in and say, look, we are interoperable, we are offering free minting for something like that. The new chains can offer maybe.
Exactly. Stargate V2, which is a bridging protocol built on top of LayerZero, one of the things that they did with their recent V2 launch was they actually created a bus. And so the way you can think about a bus is that there are a ton of different users that each want to send a message to a destination, right? And so you load the bus with each of their individual messages, right? And then ship it all at once in one transaction. And so you're distributing the cost across many more users. It gives you a lower average cost for the bridging transaction, and this leads to better fees overall for the end user. Things like this, where you get creative about how do you distribute the cost of block space and how do you most efficiently use it really are how you can optimize a lot of the bridging cost, I believe.
Yeah, talking about the messages, so how the payload is be transferred. So each application's payload transfer individually, or you create a block or something. How does it works?
Yeah, it's all being done individually. So I'll actually probably let's just go through a last couple slides, and then I think jumping into a code example might be really useful here, just so we can see under the hood what's actually happening. So um, yeah, I think to wrap up really quick, and then jump into that use case, right? This framework of being able to give applications configurability means that LayerZero as a protocol, isn't optimized for any one use case. It can be optimized for any. And so that means that any application, whether it's DeFi specific, whether it's SocialFi, gaming, NFTs, whether it's just moving raw data or identity, KYC, you can use either contract standards that LayerZero provides to make it easier to develop, or broadly any smart contract interface that can interact with this LayerZero endpoint, emit a message using the configurations that you've set, and then deliver them to a destination chain. As of today, we are live across a bunch of different, sub verticals within the space, whether that's like traditional financial services, whether that's with enterprise users, whether that's with stable coins, token bridges like Stargate, gaming protocols, DeFi, because the protocol is so agnostic to the security mechanism that the application uses and how you orient that application, it means that we can, service a lot of these applications that need different identities essentially from cross-chain messaging while still giving you a consistent interface to constantly look back to. The endpoint ultimately will always be the contract that you send messages from and you send messages to and that you receive messages from. And so that gives you a good framework of understanding how to actually interact with this cross-chain protocol. How do I configure these new kind of security mechanisms without needing to go and learn myself an entirely new bridging protocol? And how to incorporate it safely within my application without having to kind of reinvent the wheel in that sense. As of today, this slide is actually out of date. I need to update this one a bit more. LayerZero is live across 70 plus blockchains, majority of which right now are EVM equivalent, but I believe as of 2 weeks ago, we launched live on Solana. The Solana endpoint is currently live, so feel free to check that out. And ultimately, the goal with this kind of interoperability standard, right, is that not only can we service public networks, but also private networks and connect them in ways that unlock new application use cases, not only between public networks, but also between these private networks that are interested in creating safer ways for users who are afraid of crypto or don't quite understand it to interact more with the blockchain in a controlled environment on their chain, but still tap into the available resources that are freer on a public network. Ultimately, if you want to start developing on LayerZero, feel free to just scan that QR code. But if not, I'm going to actually jump into some of the code really quick to answer that last question. I have 3 kind of examples that I hope cover broadly some of the questions that we had earlier in the chat. The first one that I'm going to go through is a ping pong contract. If you're wondering what this repo is, that QR code that I sent, it should link to a CLI tool that LayerZero has produced. This CLI tool, if you look, has just spun up a repo that has both Foundry and Hard Hat contracts in it. So you can use Foundry or Hard Hat, whatever you want. It does not matter. And one of the interesting things that you can do with this example is you can utilize this test helper that we've built. This test helper lets you simulate a cross-chain transaction entirely in your unit test. This is not spinning up a local network with Anvil. It's not using any local blockchain nodes. You're actually just using the Foundry unit test and some contracts that we've spun up to mock the endpoint behavior, mock the verification step, and then mock the execution. But at a high level, want to take a step back. We had a question earlier, which was, how do we actually form these inputs and who's the caller that sends these messages, right? At a high level, this contract is very, very simple. It's only inheriting this OAP standard that we have and this library called options type 3. This library, don't worry too much about it. This just allows me to enforce the gas amounts that I want users to pay on the destination chain. You can see here that in this contract, I've defined a data variable, nothing received yet, some random message types that I want to use. In this case, I want to send a message to a destination chain for message type 1. And then this send ABA, which means I want to send a message to the destination chain and then have that destination chain ping back, right? So I want it to send a return call back to its sender to notify it that it received the message. The way that this contract works at a high level, super straightforward. All I do is in the constructor, I provide the endpoint address that I'm going to use and the owner, pass that into my OAP library, also provide it into the Open Zeppelin ownable. This encoding I'll jump to in a little bit. And there's 3 main functions to really pay attention to. There's quote, there is a send function, and there is a receive function. The way that this send function works is it'll take the destination endpoint ID that I want to send to. It will take the message type, whether it's just send or send ABA, And then it'll take a string actually as a message. In this case, I just want to send literally a message to store in storage on the destination chain. And then some extra options. I'll jump into this a little bit in a sec, but all this function does is when I call send, it will invoke the OAP's send method. Like I showed you in the slides, this just calls endpoint.send with the message value I need, checks if the peer is valid for that destination, then sends the message. But the really interesting bit, and I think what people are probably more curious on is, we have this method for sending outbound, right? It's payable by the message sender with the message value that they give. How is it being received? Well, on the destination chain, this contract will also be deployed. So I'll have two instances of ping pong A and ping pong B. The way that ping pong will work is that when that message is sent, verified correctly and delivered, this LZ receive function will be invoked from the endpoint directly using that receiver interface. And this function will basically define, okay, there's a string to data, a message type, and then some of these execution options, and we'll decode it from the bytes that I've encoded on the source chain. What it will do then is we'll check, hey, is this message type a return call? It will, fill in what the new message is, and then it will send that message off using the origin that's provided as a struct here. It will pull, hey, who was the sender? Where did it come from? It will pull the new message and who to send it to. In this case, send is the message type. And then some of the execution options that I want to pass to the destination chain. So altogether, when I call send, it will send a message. This will be received. It will call internally another send function, and this will go back to the returning contract. In practice, this will look a lot simpler actually in the Foundry test. So this setup, super simple. I'm just mocking, there's a chain A and a chain B that I'm working with, deploying mock to endpoint A, endpoint B. And then in this test ABA, you can see here that I have these settings for enforced options. This is the part where I was talking about the gas limits. In this case, don't pay attention to the gas amounts here. Within Foundry, it's not actually accurate of a real chain in terms of how much way it will cost. But the idea should get across that I can define how much gas I want every caller of send to pay. If I just have them send one message to point B, it will cost 50,000 gas that I want to deliver to the destination chain. For message type send ABA, I will have them pay up front for, let's say, I actually don't need this much, but we'll just say 600,000 and 200,000 worth of message value, right? Similarly, on the receive side, I can do the exact same thing. So if I'm receiving a message back from B to A, I want to pay 50,000 gas. And this gives us kind of a setup for the gas amount of the gas limit here, and the message value. From there, once I've kind of set up the settings how I like, all I'm going to do is call the set enforced options function on the sender contract and the receiver. From there, generate a quote for how much it's going to cost. The nice thing is that you can just generate this quote off chain if you like. So generate how much it's going to cost for sending from B to A. And then I can pack that amount back into my single sending contract here as an option, quote it again, and then pass that quote as the message value to my user A. The way that this function is essentially being called is that I'm pranking as a random user. I am calling send with message value equal to this quote that I generated for the total gas cost. The quote contains the source chain gas cost. It contains the source chain cost plus the price of gas that I want to send, plus the fees for my chosen security stack. So, and executor. So this is kind of what this quote function is actually doing. It's taking all of these inputs, taking the payload I'm sending, the destination I'm sending to, and these execution options and figuring out what is the total cost of sending this message. From there, this just verifies that, hey, I'm delivering the packet to the contract on chain B, and I'm verifying the packet and delivering it to the contract on chain A. With that, I'll run forge build, make sure it builds correctly. Yep, no changes. And then run this contract here. And we'll actually be able to look at the stack trace here to kind of see a little bit deeper what's happening. You can see that within this stack trace, the ping pong contract on chain B is returning for me. Chain A says hello. And the ping pong contract on chain A is saying chain B says goodbye. So we know that the data variables, that's what's being called here in our test. This data field that's just a string, right, has been updated correctly by our different contracts on the unique chain, and then updates the state and returns state correctly. So the neat thing here is that although this example is relatively simple, there's a ton of different use cases you could think for why you might want to have return calls, right? Whether that's, potentially doing some type of KYC check, whether that's doing a DeFi operation where you want to, let's say, pay for some asset that's available on chain B using chain A's tokens, and then have it return a asset from that chain to you. We have a lot of partners, for example, that create omni-chain NFTs. And so if you had an omni-chain NFT marketplace, you could pay for an NFT and have it delivered to a source chain for you if it's not currently on that chain at the given time. A lot of things with this kind of back and forth pattern mechanism can be used and done. Real quick, I'm going to stop there and just pause for questions if there's anything about this kind of design pattern or about the protocol too. Happy to jump into that also.
Yeah, I think that was a great example. So I think, yeah, everyone's
awesome.
Probably, yeah.
Awesome. If that's the case, I'll jump in then to another one. Really quickly, just I don't want to go too far on our time here. Yeah, so this is another interesting example that we've deployed recently. So one of the use cases that you might want to have with a cross-chain protocol is rate limiting, right? The ability to say, okay, I'm moving this amount of tokens from chain A to chain B, but I don't want all of them to be able to move at once. Let's say I want a hard cap on how many tokens can move. This, what we call an efficient rate limiter, is a way for you to basically specify that there is a max amount of tokens that can ever be in flight, right? And within this contract, the way it works is it will calculate from the rate limit the amount that have been sent, when it was last updated, what the limit is, and this window of decay. And so this graphic here kind of shows you that over time, if let's say the max cap is 100 tokens, it will decay as this amount in flight increases or decreases, right? So if 100 tokens are in flight, actually, I probably should reverse this graphic. The main idea is basically that you are limiting the number of outbound tokens that can be sent at any given time, and that if someone sends a massive balance of, let's say, 100 tokens, right, that's the max cap. The way it will work is it will slowly decay and allow you to send a little bit more before it hits that max limit again. So you can see when 100 tokens have been sent, no tokens can be further sent again. At the next point, the cooldown is applied a little bit. So maybe like 10 tokens have now freed up to be transferred. A few seconds after that, maybe closer to 30, and so on and so forth. You have this decay rate. But the more interesting bit is probably what you guys are thinking about for the cross-chain side. So this rate limit can apply in a lot of different ways. One of the unit tests that I have here is basically checking that, yes, the test receive amount will fail when you send too much. Actually, I want to jump into one maybe a little bit simpler just so we don't spend all our time going through this custom logic, right? So for the OFT transfer, perfect. Basically, all I'm setting here up higher in this test contract is what the rate limit actually is. in this case, I'm saying that the max amount of tokens that can be sent outbound is 2 to this chain, and there is a time limit of 60 seconds, right? What this will do is in this send function, it will first create this struct of send parameters. This is a very standard struct for the Omnichain fungible token contract. You'll probably recognize a few of these params. The first is that it is obviously the destination we want to send to. The second param is who is the address receiving this token on chain B. This can be an externally owned account, could be a contract, doesn't matter. You can see here, this is the amount of tokens to send. This is the minimum amount of tokens to send. And finally, again, those execution options. And then 2 other variables here. This one is our composed message. So remember, I could send, if I wanted to, another external call to be executed after this token transfer. I won't do it just yet, but we will look at that in a moment. And then this last one here is a OFT command, also bytes. Won't go too much into the OFT commands. It's another advanced function that you can use within your OFT logic to basically have extra checks within your receive side logic to, invoke different function calls within the LZ receive call itself. But again, the way this send test works is for our OFT that's deployed on chain A, it's just an ERC20 token. We generate a quote using our send params. We store it as a fee. We do some asserts just to make sure that the balances are correct. And then when we call send, what's happening here is we are going to send an amount of value using that quote we generated. We're going to pass in that send param struct that tells us who we're sending to, the amount of tokens, all of that, the fee that we're going to pay. And then we are saying that it's payable to address this. In reality, probably message.sender would make more sense here just because there's an external user calling it. And then testing that after we've called this send operation that calls the endpoint and emits the message, we verify the packet through and check that did the balance deduction happen as expected. Afterwards, we then check, all right, is it going to allow us to send the same number of tokens within that correct limit, right? So if we look at this test, we can see we're pranking again as the user, calling send, verifying here, skipping ahead, 61 seconds, pranking, sending the message, and calling a second time. And so if we do forge test, match test, actually I'll do match contract just to make sure we're hitting this one. Rate limit mock, and then match test. We can see for this one, test send OFT succeeds after waiting limit. Nice. We can see here test passes, but more importantly, I want to show you what's actually happening. We can see here that basically this test is succeeding because we're sending a token amount, right, to a destination chain. We are asserting that, hey, this is the initial balance for both users, the balance of the OFT for user A on chain A. And then similarly, the exact same balance of the OFT for user B on chain B. When we send those tokens, we are doing a check here to make sure that the amount sent is debited correctly, right? And then also checking that the amount sent is credited correctly. And then just enforcing that rate limit actually is happening the way that we expect. So very, very useful kind of way to think about it. I know we're kind of running low on time here, but I want to go through one last example too, if we have the time for it. Are there any questions though, really quickly about, the rate limits or, how you can implement this yourself? Nope. Okay. Awesome. I will keep jumping along then. Last one is no more mock testing. I actually want to look at something that is already deployed. Actually, I will go to really quickly here. Give me just 2 seconds. I'm going to pause my screen share for a moment just so I don't bore you with all of the files on my desktop. But there's a really interesting example of that composed message logic that I wanted to show off as well. Mainly this idea of being able to transfer a token, swap it for some amount, and then stake it. So I'm going to go to a contract that I already have deployed here. Inside this, you can see again, this is the CLI repo I have before. In here, I have some fun other contracts that I've been working through, but these are not finished yet, unfortunately. But some of them are, which is this ERC20 mock. Think of it just as a standard ERC20. This swap mock, the way that this swap contract works is using that composed interface and then just a standard OFT. So the way that an omnichain fungible token works, as I've kind of shown before, right? Just like ERC20, under the hood, what this contract is doing is very, very similar to the original ERC20 token. So if we jump in here, we're just inheriting some contract logic for how to interact with the LayerZero protocol and the ERC20 contract, pulls in some familiar methods like token to show the token address, and then has this debit and credit logic. And you can see in here that, whenever a message is sent, this debit function will be invoked, which calls the ERC20 burn method to burn that amount from the source chain. And then once that message is verified successfully, delivered to destination, will get credited, and that mint method will be called as well. So returning that amount of local decimals delivered. I'm going to go pop into a pretty useful utility that I have here. I've deployed this already a couple times, but I deployed it on Arbitrum Sepolia and Avalanche Fuji. And we're going to pop to LayerZero Scan. This might not work from my view, at least, so I might have to paste this link over to you guys to see. We're currently a little bit rate limited from our side, just from people spamming the scan interface. But I will pop over and send this in chat here. So if you take a look at that scan interface from your guys' side, you'll see a list of 38 different messages, right? The important thing is not really just the list of different messages, but showing you the interface of multiple different contracts on Arbitrum and Fuji working together, and kind of seeing, where those messages are being sent. It's really handy because you're able to see clearly from that interface the message payloads, the execution amounts, how much gas is being paid for the receive logic. And then within the actual code snippet, the thing that I think will be most useful for you guys, if we go in here and look a bit deeper at the composing mock, right, this swap, in reality, you probably wouldn't deploy this contract outright with an OFT. But what you might do is have this call some other bridge interface for some type of token that you want to transfer. The way that composing works is that you just have to inherit this composer interface. And what it will do is it will take in the ERC20 token address that I want to, let's say, swap for, right? It will take in the endpoint address that is expected to receive messages from on the destination chain, and it will take in the OAP address. Essentially, what's happening here in this flow is that there's a function called lzcompose. The way that the workflow is happening is that someone will call OFT send, right, which will send a message to your specific security stack and also your executors, right? Once that message is verified, you can think of it as being endpoint.lz received by the destination endpoint. And then that is again delivered to the OFT contract and calls the OFT methods lz receive. And so within this workflow, after the message has been successfully delivered, a secondary call is made within OFT.lz receive. I will make a call to an endpoint method called sendCompose. what send compose will do is it will, again, store the message back in the current endpoint for that chain, and then it will re-emit that message as a separate transaction that the executor will invoke by calling endpoint.lz compose. And that's what's being executed here. This endpoint.lz compose is calling the composer's lz compose method. And so in this example, it's very, very simple. All it's doing is first checking, hey, is it coming from the OAP I expect from the message? And is it coming from the endpoint that I expect? And then decoding from that composed message a receiver for these tokens that I'm about to swap. It is then decoding the amount that was received to this contract from the OFT transfer, and then just doing a quick ERC20 safe transfer from. You can think of this as like a lockbox contract for all intents and purposes. Ultimately, this logic not super extendable itself directly into an implementation, but I would think of it as a good stepping stone for understanding how composability works, right? The idea is simple, that I can send a token from my chain A, right? So a.oft send, verify the message, receive the tokens. Those tokens get delivered to this contract. I guess I'll put that here. I'll composer receives OFT token. And then in this secondary workflow, it is swapping that token for this nested ERC20 that's in this contract. And so this gives you a very interesting way of kind of diving through the different compose steps that you can look for. What I'll do is, because I don't have the ability to show you on scan right now, I'll actually just pull up Arbitrum Sepolia scan really quick. Oh, I had it already for me. Perfect. There. Pull up the swap mock contract. It is verified on the Block Explorer. You can see that this one is slightly different. I've changed the interface ever so slightly in this bottom contract here, I believe. Yep, swap mock. You can see here, I originally was encoding an amount and an address as an example. The current code uses actually this method internally called amount LD, just to know how much from the message itself needs to be delivered. But the most important thing about seeing this Block Explorer example is the actual ERC20 token transfers. You can see here, there's this repeat pattern of in and out. Basically, what you're seeing is whenever an OFT is received on the Arbitrum side, it is being sent into this contract. And then at the exact same time, one token is being sent out, this mock ERC20. And so we have this mock OFT as the input, the mock ERC20 is the output over and over and over again. And this kind of gives you the supply line logic that you might expect, right? If you need your application to, let's say, not revert from the receive logic, if, let's say, this swapping function fails, you can know that they are separate transactions entirely that have their own gas limits, their own message values, and are entirely controllable by the application. I'm going to paste this here, and then I think probably just wrap up for general questions from anybody, if you have anything else.
I think we've got time for just one question, because I think we're right at time.
Yeah.
So Babu, go ask your question.
No, it's not a question. Just it is very good.
No. I do not have a question. I was just making sure you all knew that. Yeah, we're right at the absolute end. Anyway, over to you, Babu.
Yeah, so all good. The last presentation was really good. So one thing, this recent trend of using the intent to send a message. What do you think? So in this case, we have a latency of both the chains to come to consensus and all those things. The intent case, the latency is taken away, and somebody is taking care of your transaction and sort of giving you the token on the other end. What do you think about these two methods compared to that method?
Yeah, I think intents are interesting in the sense that it requires the prover and the, oh, sorry, can you hear me okay? Nice. I think it's interesting because the prover and the filler for those intents really do matter. A lot of kind of the speed that you see for some intent-based protocols is they rely on finding someone to fill the order relatively quickly. And the actual method for how you select who is filling that order on the destination chain isn't exactly clear in a lot of cases. There's a lot of room for potential centralization vectors within how you prove and really what messages are delivered first, who is filling the messages out of the available stack of fillers. And I think there are, in general, probably some scalability concerns, I think, for one, large volumes that potentially, might drain the filler accounts. In general, the method for, I think, most arbitrary messaging platforms ends up being a little bit slower, but tends to be more cost effective too, I think, on the long tail. Part of it is this ability, one, to spread out cost between the source and the destination. But with LayerZero, I think with intents, it's difficult because you could reasonably make a case for example, building like a DVN that does intent-based model filling, right? Getting someone to look for a message and maybe optimistically, approving it until someone, flags it as invalid. But there's just a lot of, I guess, centralization risk that we personally don't see as being as solvable, I guess, at a large scale, to answer your question.
Yeah, thank you. So the last part you shown us was really good. So that makes sure that the functionality on everything works very well. It will be good to have some threat model in a sense where what are the possible things can go wrong in between, and then testing that case will actually prove. So all the things I've shown is all the functions work very well, but a lot of the times there is a lot of other factors that in between can go wrong. So that
Definitely.
that testing will be really helpful to make this really work. Thank you.
Yeah, appreciate it.
Yeah. All right. Well, look, thank you for coming along today, Matt. That was a great talk. Everyone, in 2 weeks' time, I'm going to talk about random numbers. So, yeah, look, thank you. And yeah, thank you again for a great talk. And have a great day, everyone. Bye-bye.
Thank you.
Thanks, Peter.